I show the slide first. Okay, I start. A very good morning to our examiner, Encik Firdaus, project coordinator, Dr. Rabita, and our lovely supervisors, Dr. Aliaa and Dr. Roseliza, and my fellow classmates. We are from Group 2 and pleased to welcome you guys attend our final stage of IDP presentation. We have assigned by the title, namely Design of UHT Soy Milk Production Plant since last semester. And first, I would like to introduce myself first. My name is Sin Yee and I am the project lead. I have worked closely together with my other three friends who are Atma, Farzana, and Danish. Without further ado, let's pass the ball to Danish and he will explain about the design objective and basis.
Now I'm going to proceed with the process involved in our plant. First is the storing of soybean where we applied the first in first out method. Next we have two-phase grinding. The first grinding is coarse grinding, producing soybean slurry when mixed with hot water to inactivate the lipoxygenases and thus improving our extraction of isoflavones. Next one is fine grinding for greater extraction. Then we proceed with fiber separation where we remove the okara using the decanter centrifuge due to its efficiency in continuous okara discharge. After that, the black soy milk will undergo microfiltration to further refine the milk by eliminating the impurities and suspended particles from the soy slurry. Then the soy milk will undergo the activation of enzyme process, which deactivates the trypsin inhibitors, causing the denaturation of protein that prevents them from inhibiting trypsin action. Then the soy milk goes to the mixing process where all the other ingredients like locust bean gum, our fructooligosaccharides and vanilla extract is added. Next, we move to the cooling process, which its purpose is to pre-cool the soy milk before homogenization prevents excessive temperature rise from mechanical energy conversion. Then by utilizing the two stages of homogenization after that, This will force the protein clumps and fat globules to break down into homogeneous particles. Then the soy milk will undergo UHT treatment to lengthen the shelf life of the black soy milk. Next one. Then the treated soy milk will enter the aseptic holding tank with pre-sterilization and control conditions. This will avoid the contamination and maintaining quality. It will also serve as sterile buffers between production and filling and keeping product sterility. And finally, the soy milk will be packed with aseptic filling technology, which entails in sterilizing packing material. Then the residues will be removed with a blast and hot drying. Next, so this is our process flow diagram. From the top left part is stream 1, where we receive the soybean that will be put into silo. Then for the second stream, it is hot water at 100 degrees Celsius that will be mixed in for coarse grinding. The third stream is first stage grinding, the slurry. And the fourth stream, the water at room temperature will be added for fine grinding. 5, it is a mix of slurry and water. And for stream 6, it is a fine black soy milk. And for stream 7, the okara will be separated from fiber separation. And stream 8, okara will be gathered in a tank. And for stream 9 here, on the bottom left, it is separated black soy milk that will enter the next process. Next one. For stream 10, as you can see at the bottom middle, it is black soy milk that enter microfiltration membrane. Stream 11 will be the microfiltered black soy milk. 12, fine okara that is gathered in the tank. And 13, the enzyme deactivated black soy milk stream. And for stream 14, 15, and 16, it is where I will add locust bean gum, fructooligosaccharides, and vanilla extract. For 17th stream, it is our mixed black soy milk. And by the stream 18, it is cooled down black soy milk. Next. For our 19th stream, it is a homogenized black soy milk. And stream 20, it is a black soy milk entering holding tank. And stream 21 is black soy milk entering the UHT treatment. Stream 22, it is UHT treated black soy milk. And stream 23, it is black soy milk that will be put into aseptic holding tank. Stream 24, the black soy milk will be filled in aseptic packaging. And lastly, at the top right, it is our packed black soy milk product.
Okay, going to introduce you guys about the sustainable development. Our main concern for sustainable development is about how to reduce the production of okara, because okara is a solid waste during the whole process. So we want to reduce the production of the okara to achieve the sustainable production. Okay, there are a few ways to reduce the production of okara. First is double grinding. We apply the double grinding method. First is coarse grind, second one is fine grind. We apply these two double grinding because we want to increase the surface area of the soybean being exposed to water. Henceforth, the particle size of the soybean will be reduced because the surface area increase and the water absorption will be decreased as well, and the moisture content will be decreased also. And overall, the weight of the okara produced can be reduced. Second one is we exclude the soaking process. There is criteria when removing the soaking process. The criteria is we need to add on the hot grinding. This one we did apply in our practice also, because hot grinding mixed with the soybeans mixed with hot water with a few minutes, it will soften the soybeans and then faster the size of reduction. Then when bring to the following process, it will be more easier. And we have research show that the energy consumption by excluding the soaking process can be up until 20 to 30% reduction. And the okara waste also has reduced. And then the third method is we apply the heat exchanger to utilize the heat recovery system. Uh, there are two different type of UHT treatment. One is direct UHT and another one is indirect UHT. Direct UHT energy consumption is much more higher than the indirect because the steam is injected directly to the soybeans, to the soy slurries. Therefore, it apply the high energy consumption. Whereas the indirect is using heat exchanger, a tubular or plate to exchange the heat between the steam and soy slurries. Therefore, we can achieve the energy saving and cost saving also and reduce the greenhouse gas emission. There is one concern about the new technology we found out, which is applying the UVC like pasteurization can also be lower in the energy consumption. But this one we didn't apply in our practice because we think we're not sure about the mechanism right now. But this is the current that show. So for the recovery system, we also apply in the Super Pro. You can see that from the video, we already applied the double grinding, coarse grind, fine grind, and then we exclude the soaking process from storage. Then we enter the hot grinding process. And then after that, you can see figure 3.2, we apply the energy recovery from the Super Pro designer. So the homogenize is the cooling part, and then we'll link to the enzyme. We'll exchange it from the enzyme because the enzyme process is heating process, and then sterilize is means UHT treatment. UHT treatment in Super Pro designer, our software got three phases. It won't directly heat up until 140 degrees C. The Super Pro will slowly heat up until 140 degrees C. So first stage from the 68 degrees C will heat up to the 100 degrees C. Preheat temperature is 100 degrees C. And then from 100 degrees C, we will heat until 140 degrees C, which is the UHT desired temperature for a few seconds. And then it will drop back from 100 degrees C until our room temperature 25 degrees C. Hence, the cooling stage for UHT process will be linked to the heating process for the sterilization. And then we also got try practice this energy recovery to match the cooling and heating steam. And we can see that from figure 3.3, this is before we applying the energy recovery from the Super Pro. The gross margin, ROI, and IRR got increased after we applying the energy recovery. Also, payback time also decreased slightly compared to before we apply the energy recovery.
Next, I will continue the presentation with the equipment. So this table summarizing equipment selection for two processes, which are microfiltration and UHT. Table 4.1 details of selecting the equipment. This indicates the table contains specific data used to choose equipment based on the certain properties. So these are the values that we get from Super Pro Designer. For inlet total flow rates, the mass flow is the weight of the fluid passing through the system per hour, while for the volumetric flow, the volume of the fluid passing through the system per hour. For outlet total flow rates, it is the flow rates describes the output of the system after the process. And then the equipment data describes additional specifications of the equipment. For microfiltration, the membrane area, it is the surface area available for filtration is 11.579 meters square and max membrane area is 80 meters square. For UHT, the max throughput, the highest volume the system can process is 100,000 liter per hour, and then the rated throughput, the operational flow rate is set at 239.95 liter per hour. Next, these are the comparison equipment for microfiltration. For filtration of Soymilk, there are two common machines that are used, and comparisons of the two are made to select the best machine for the plant. Table 4.2 shows the comparisons between the equipment. For the properties, the MWCO, molecular weight cutoff, it is for microfiltration is more than 100 kilodaltons, meaning it removes larger molecules and particles. And then for ultrafiltration, 1 until 500 kDa, meaning it can filter out much smaller molecules compared to microfiltration. For the pore size, for microfiltration 0.1 until 10 micron, it is suitable for filtering larger particles, or for ultrafiltration 0.01 until 0.1 micron, allowing it to filter smaller particles. The species rejected for microfiltration, suspended solids, bacteria, colloids, fats, and others, and ultrafiltration, suspended solid, bacteria, viruses, colloidal silica, polypeptides, proteins, antibiotics, and others. Next, the comparison equipment for UHT. Comparing the operating characteristics between the two heat exchangers, the tubular heat exchanger is more suitable for UHT treatment as it is more efficient in heat transfer, which is crucial for UHT treatment. Table 4.3 shows the comparisons between the equipment for UHT process. First one, construction. For tubular heat exchanger, it consists of an outer shell and a bundle of tubes, while plate heat exchanger made up of a series of thin metal plates sandwiched between rubber gaskets. And the cost for tubular heat exchanger less expensive than plate heat exchanger, and the efficiency for tubular heat exchanger more efficient than plate heat exchanger, which greater than 90% are achieved. Next, the equipment selection. Table 4.4 shows the selected equipment for both processes. The equipment for microfiltration is membrane filtration system and UHT tubular heat exchanger. The cost for 1 unit membrane filtration system is 3,198 and 27 cents, while UHT 11,795 ringgit. And the equipment properties for microfiltration, membrane material is PES, size of membrane 52 mm, membrane area 0.58 meter square, and the capacity 10,000 liter per hour. For UHT, the holding tube diameter 0.569 cm, holding tube length 26.68 meter, makes throughput 100,000 liter per hour, and rate throughput 233.04 liter per hour.
Okay, this is some basic calculation from our group. Because the calculation is too lengthy, I just summarize. We look for the microfiltration first. So the diagram is we get the info from the Alibaba supplier and they provide the quotation, and then we select the parameters from the quotation. Okay, there are many lengths for the membrane, and we choose the length for the membrane is 1,200 millimeter. Pore size is 8 mm, and then number of channel is 19. And then spacing between the channel means the thickness of the membrane is around 4 millimeter. So for one module, the surface area, we use pi dl to calculate, and we get 0.57 meter square. For surface area for the whole microfiltration system, we use AW stand for whole surface area, JTL. J stands for the heat flux, T is the filtrate time, L is the length of the membrane. So we get the result 18 meter square. To calculate the number of module needed, we just divide the surface area for whole microfiltration membrane system for one and divide by the one module. We get 32 modules needed for microfiltration. For tubular heat exchanger, also we select the parameters based on the TEMA. Outer diameter will be 19.05 millimeter, inner diameter 15.75 millimeter. Length of the tube will be 4.88 meter. Then to calculate the one tube heat flow area means the surface area require the heat to pass through the tube is using the Q over U is using the Q divided by U multiplied with the temperature difference, and we get 2.43 meter square. So area for one tube is we using the pi multiplied with the outer diameter and length, we get 0.29 meters square. So to find the number of tube per pass, to find the number of tubes, we divide both of it and we get 8 tubes, and number of passes we set as 4 passes because the more the passes, the more the energy transfer in the tubular heat exchanger. So we just divide the 8 tubes divide by 4 passes and we get 2 tubes per pass. Then it's time to show our drawing, and this is our overall design by using the AutoCAD to draw it. So we look at figure 5.1 first. This is the overall design for microfiltration system. We have control panel on our right side and the filter on our left side. And then there are 32 membranes there and 32 L-shaped pipe to connect the top. And then for figure 5.2 is the roughly design for tubular heat exchanger. There are 8 tubes there, and then the buffers will be 20. It's not meaning that the more buffer in the heat exchanger will be very good, because sometimes it will easily cause the fouling issue in the tubular heat exchanger. And yeah, but moderate buffer, number of buffer is good enough because it can allow the circulate liquid in the tubular heat exchanger. Then this is the orthographic view from microfiltration system. We have top, front, and side view. And if you compare the actual calculation, it got slightly difference. For example, the length is 1.2 1200 mm, but here is around 1300 m. And this is the one tube heat exchanger orthographic view.
Next, I will explain about the PNID of our two selected equipment. This one is for the UHT process. By this time, the throughput of soy milk entering is around 240 liters per hour. Firstly, on your top left view, the raw soy milk will enter through a feed line with a level transmitter LT01 and level controller LC01, ensuring the correct amount of soy milk. Then the steam enters the heat exchanger where a temperature indicator TI01 monitors its heat, and temperature controller TC02 adjusts the steam flow for accurate heating. The heat exchanger will raise the soy milk to desired UHT temperature. A pressure transmitter PT01 and controller PC01 monitor and maintain pressure with a pressure relief valve for safety. As the treated soy milk exits, its temperature will be monitored by temperature indicator TI02 and transmitter TT03, while a controller TC03 ensures it stays at the correct temperature. The second one shows the PNID for microfiltration. The microfiltration process has 3 main flow streams: the feed, the retentate, and the permeate stream. The feed enters through the inlet with its flow rate measured by flow transmitter FT101 and regulated by flow indicator controller FIC101 for steady input. A pump pressurizes the feed with its pressure monitored by pressure transmitter PT102 and controlled by pressure indicator controller PIC102. The retentate, which contains fiber that will be rejected by the membrane, flows out of the system, and its flow rate is indirectly controlled by feed pressure and system dynamics. The permeate, which is the filtered soy milk, will pass through the membrane and is monitored by flow transmitter FT104 and regulated by flow indicator controller FIC103 before being sent for further processing, which is the enzyme.
Next, I'm going to continue the presentation with waste handling. Table 7.1 shows the source of waste produced. So there are two types of waste, solid waste and liquid waste. For solid waste, the waste produced is okara, and the source are centrifugation and microfiltration. For liquid waste, the waste produced CIP cleaning, and the source is wastewater. Figure 7.1 shows the liquid waste handling method. There are three types of treatment method: primary, secondary, and tertiary treatment. For primary treatment, there are two processes: screening and clarifying. For screening, it is eliminates debris, sediments, and other pollutants from liquid stream. For clarifying, separate suspended solids and heavier particles from wastewater via the process of sedimentation. For secondary treatment, extended aeration process, it is reduced the generation of waste sludge, and the aeration time is extended so that the mixed liquid suspended solids remain at a concentration allowed to settle in the clarifier. Next, the tertiary treatment, disinfection. Chemical disinfectant incorporated with physical method in this treatment, and the total number of coliforms applied as the indicator to check the quality of sanitization. According to Environmental Quality Industrial Effluent Regulations 2009, there are two standards. Standard A refers to any inland waters within the catchment areas that stated in 6th schedule has a permissible level of BOD not more than 20 milligram per liter and COD not more than 50 milligram per liter. And standard B, other inland waters or Malaysian waters has a permissible amount of not more than 50 milligram per liter for BOD and not more than 100 milligram per liter for COD amount. Figure 7.2 in the table provides information on the typical composition of waste generated by the dairy and milk product industry.